talk about conjugate prior and actually some maximum likelihood map detector also today. Let me start with a very simple example here. I have x is a random variable. It's just, you can think of x is the outcome of flipping a coin that can get either 1 or 0, and we'll assume the coin can be unbiased, so it can be biased, and the probability of x equal to 1 is equal to q, and probability x equal to 0 is equal to 1 minus q. And so the goal is like we're going to flip these coins many times, so we get a sequence of outputs like xy and x2 and so on up to xn. So basically we flip these coins by n times, and then we want to estimate this probability q here. So one way to do it is to do a maximum likelihood estimator of q. So basically we we write down the likelihood function. That's basically just the probability x1 up to xn given q. So because given q, this flipping these coins here, these events are all conditionally independent. We can split into the px1 given q and so on and so forth. And then like if I have outcome is equal to x1, is equal to 1, let's say, then the probability will be q. And if it's equal to 0, I will have the probability 1 minus q. So I can summarize these two situations into one expression here. Basically, it's qx1, 1 minus q, 1 minus x1. As you can see, if x1 equal to 1, I will have q. If I have x1 equal to 0, I will have this expression equal to 1 minus q. So I can do the same for all the other pxn given q here also. And then I just group these terms here. I have q to the x1 sum over to up to xn, and 1 minus q n minus x1 sum over to xn. I can call this x1 sum to xn is equal to m here. So it's another variable here. And you can think of this m is nothing, it's just the number of times that we get a 1 result 1 here. So and this is, of course, if you see that, like as long as we know m, we know all the information regarding in terms of like trying to estimate q. So actually m here is the sufficient statistics, and it's very intuitive. Like if we want to estimate q, we don't really need to know like what's the outcome of the first coin, flipping the first coin, and what's the outcome of flipping the second coin, and so on. We only need to know that what is the total number of getting a head and total number of getting a tail. So I have this values. So I rewrite this. Just key this thing up. I have like q to m, 1 minus q, n minus m. Now if I want to maximize this expression regarding to q, I can just take the derivative here. Let me write a as m and b as m minus m. I'm trying to take the derivative here, trying to maximize this. And maximize this is the same as maximize the log of this expression, or like a log q plus b log 1 minus q here. So I take the derivative and set to 0. I have a 1 minus q minus b 1 minus q over 1 minus q is equal to 0. And then I will eventually got q is equal to a over a plus b. So therefore I will have the estimate will be just m over m plus m minus m, that's m over n. So the whole thing is very intuitive. Basically our best estimate is just the number of 1 that we get over the total number of times that we flip the coin. Okay, a problem for this maximum likelihood estimation is that if we use the maximum likelihood estimator, let's say we want to use this to predict future outcome, and let's say we just flip the first coin, and we get x is equal to 1. And if we use the MLE to estimate the Q, what we get is that Q will be equal to 1, right? In that case, that's basically saying that for sure that for the future x will be always equal to 1. It doesn't sound making much sense really. So the problem is really that like we are a bit too extreme in the sense that we trust too much of our observation. This can be solved by the map estimator instead. Basically, the map estimator is something like more, I would say, reasonable, in the sense that instead of trying to maximize the likelihood function, we're trying to maximize the posterior probability. Basically, given observation x1 up to xn, we want to see what's the probability of Q given that observation, and we're trying to maximize this probability for the Q that maximize this probability. And if we find that Q, that basically Q is our estimate. So we can write this posterior probability using base rule as this px1 after xn given Q times pq over this px1 to xn, and of course this denominator here is just a normalization factor, because in the sense that like we are trying to optimize the variables, the optimization variable here is Q, and it doesn't depend on Q. We can just ignore this term here, and we have this only. And of course, the first term here is just the likelihood function, and we know that it's just equal to Q to M times 1 minus Q M minus M. So basically, that's the thing we're trying to maximize. So now, what happened is, let's say if we have something that have a form very similar to this likelihood function. In particular, if I have a PQ here, have the form of Q to the alpha something Q to the power something times 1 minus Q to the power something, then after multiply this, the likelihood function by the prior, I still have like Q to the something times 1 minus Q times to the something. That would be very nice, because immediately I know what's the optimum value of Q. Because actually we already showed this earlier. It turns out it's possible to find such PQ here, and this actually is just a beta distribution that and the beta distribution will be kind of parameterized by some we call like hyperparameter here, alpha and beta, and basically this PQ is given by this expression here, and B alpha times beta, this denominator here is not really so important. It's just a normalization factor here. So if I multiply this by here, I have this here. I'm trying to maximize this, and we know how to maximize this earlier. Is the optimum Q is just equal to M plus alpha minus 1 over M plus alpha minus 1 plus M minus M plus beta minus 1. So we have this expression here. And by the way, this PQ here is precisely what we want to discuss here. Is known as the conjugate prior of this likelihood function here. So we have the Bolognese distribution, the Bolognese likelihood. The conjugate prior of the Bolognese likelihood is basically this beta distribution. So what we can see is for this this likelihood here, know that like Q is a parameter, M is really the random variable, and for the PQ, the conjugate prior here, Q is really the random variable, but alpha and beta are the parameters, and more precisely the hyperparameter. And we can see that like before multiplying this prior by this likelihood function, if we look just look at this prior itself, this prior distribution of Q is completely characterized by this hyperparameter alpha and beta. And now after multiplying it, basically we have this alpha and beta is kind of updated to something like alpha plus m and beta plus n minus m. It is like that, like at the beginning you have some hyperparameter, and after each observations and updates, if we want to estimate the parameter of the model, that's basically Q here, we will just have this hyperparameter is modified by the observation. So computationally it will be very simple. Okay, so let's say actually with this alpha hyperparameter, what we know is not the exact model, but we only know the distribution of the model, because given the hyperparameter, we're basically saying that the model is having, or like the parameter of the model having a distribution, some distribution. And if we want to predict the next outcome, or the next x here, in this case, for example, we want to know what's the probability of next x, what we need to do is really need to integrate over all the parameters with the distribution specified by the hyperparameter. So therefore, we should integrate this p, for example, this px equal to 1 given alpha beta is equal to px equal to 1 given q times pq given alpha beta. And we're going to integrate over q. And if we do the integral here, of course this is just equal to q, and this is the pq alpha beta is really the beta distribution. We know the mean of beta distribution is just equal, so this is really compared to the mean of the beta distribution, and we know that the mean is just equal to alpha over alpha plus beta. So given the hyperparameter alpha beta, we know that the next the probability of getting the next outcome to be 1 would be just alpha over alpha plus beta. Now let's look at another example. Let's say instead of having only 2 outcomes, like alpha either 1 or 0, let's say we have a categorical distribution. Let's say we have a system that basically can have k different values, k different outcomes. It can have probability getting outcome is equal to 1 with probability p1, and outcome equal to 2 with probability p2, and so on and so forth. So of course I have this sum over p I equal to 1 to k is equal to 1. So, and let's say I have like n observations here, x1 up to xn. This maybe, for example, maybe I have observation 1, 2, 1, 3, and so on. I get a k here for the last one. And the probability, if I given these parameters p1 up to pk here, the probability of getting a px given p1 up to pk, okay, is just equal to p1 exponential x equal to 1. Here, this is just an indicator function here. So if x is indeed equal to 1, I will have 1, otherwise I will have 0. So I write like this, basically just to, actually it's just to summarize, kind of a convenient expression to summarize all case situation here. So if I have n observations here, x1 up to xn, then the probability like px1 up to xn given p1 up to pk will be basically just p1 m1 times p2 m2 and so on pk mk, where each of these m is basically the number of times I get a particular outcome, or more precisely, m2 here is the number of times that we get an outcome is equal to 2. So now if I think of the conjugate prior, I would like to have, again, like when we think of this likelihood here, this m1 up to mk here, these are really the variables, these are the random variables, and p1 up to pk are the parameters. Now if I think of the conjugate prior, I want this p1, p2 and so on are the variables, and now I want to have a distribution that have this p1 and pk have as variables and has a form similar to this guy. Turns out we have a distribution like that. It's basically a Dirichlet distribution. We have p1, a Dirichlet distribution with parameter alpha 1 up to alpha k will be like p1 alpha 1 minus 1 and so on and so forth, like this guy here. Again, I have some normalization factor b alpha is given by this here that we don't really need to care too much about that. So if we are given initially this hyperparameter, let's say we think of this is the prior, let's say we have like alpha 1 up to m alpha k, and let's say this is like after some observation, after n observation, with basically the observations like m1 up to mk. So what we have is that just the hyperparameter will change from alpha 1 up to alpha k into alpha 1 plus m1 and to alpha k plus mk. So again, like given this hyperparameter, we can find the mean and so on. Basically, what's the probability that our next outcome, for example, will get a j, px equal to j given alpha 1 alpha k to alpha k. What we need to do is, again, we need to integrate over all the parameter, p1 up to pk. So we have this is equal to probability x equal to j p1 up to pk times p1 up to pk alpha 1 up to alpha k. And given p1 up to pk, we get x equal to j, the probability is just equal to pj. And if we look at that, this is basically a Dirichlet distribution, and we are really, this is just computing the expectation of the Dirichlet distribution for the j component. So we can just, okay, honestly, I'm not quite sure how to do this integral, but you can just look for the mean for a Dirichlet distribution. We know that it's just equal to alpha j over alpha 1 plus up to alpha k. So that's how we get the average. No, not average. The probability of the outcome given the hyperparameter. Okay, before I end, I want to do one more example here. Let's say we have a likelihood function is a normal distribution. We have a source that is normal distribution, normally distributed, and we have basically sample from this source, and assuming that we know the variance but we don't know the mean, so we're trying to estimate the mean. And it's quite well known, the normal distribution is given by this expression here. And now remember that, like, for the original distribution here, x is the random variable, but now we're trying to estimate the mu here. Now think of mu now as the random variable, and then in this case we see that, like, even if we think of mu is the random variable, this is still a normal distribution, because like x and mu here is essentially symmetric. So that means that the conjugate prior of the normal likelihood function with a fixed variance is still a normal distribution. So let's pick p mu, the prior, have this expression here. Basically, this mu prior have something like this normal with some mean mu lot and some variance similar square. So with that, we can try to find the posterior probability. Basically, multiply these two here, and I have this. This is the multiple, and actually we don't need to care too much about the constant here. This is just a normalization factor, and we can focus on the exponent. And here I just expand these two terms here, and also, like, I don't need to care too much about the terms without mu. The terms without mu, again, is just a constant. Essentially it's just a normalization factor eventually. So let me just expand the terms with contain mu, and I pure n to sigma square sigma log square, so I need to multiply the first two terms by n and over sigma log square over n, and the second these two terms by sigma square over n. So I have this here, and then just group the terms. I have this sigma log square plus sigma square over n times mu square, and I have this multiplied by mu. So then, like, actually by computing square, we can see that the mean of essentially what we have is we will have something like this p mu something is equal to exponential minus this exponent. Let's call this w, something like w mu, and times some constant, I don't care. And I can see easily just from this here, this exponent here, the portion of exponent here, the mean mu, the mean of this distribution, will be just equal to this over by this guy here. I can write this here, and the variance of this distribution is just this term here, sigma square sigma log square over n times this guy here. Because basically we have for Gaussian distribution or normal distribution, we have mu times some mu, let's say mu pi, and 2 sigma pi square. And we have this, basically is the mu pi here, this is the sigma pi here. So in any case, like in any way, what we have is basically, if we have some hyperpriors to start with, like some mu naught and sigma naught, after n observations like x1 up to xn, we will have this, the mean got updated, the estimated, the parameter, the mean of the hyperparameter get updated, and also the variance of the hyperparameter got updated. And actually we can see that the variance will already become smaller because like n over sigma square, we add these terms here, and we always have this thing is less than or equal to 1 over sigma naught square. And also, like if we have more observation, this gets even smaller. Like if this is bigger, this part is bigger, then apparently this is smaller. And also, like if the variance of the observation is smaller, then we also have this sigma naught will become smaller faster after each observation. All of this is quite intuitive. Maybe all we can do also do a sanity check for this mu here. For example, if we have xi, all the observations are mu naught, then this sum of mu naught over n here will still equal to mu naught. Then this is just equal to sigma naught square per sigma square over n times mu naught. So this sigma naught square per sigma square over n will get cancelled, and we'll just get mu naught. So of course, like if for each of the observation, if all the observation is equal to mu naught, apparently the hyperparameter, the mean of the hyperparameter will not change.